Hello, and welcome to today's webinar with Owens Corning. My name is Jessica Casey, and I'm the editor of LNG Industry. Today's presentation is titled A Passive Approach to Pool Fire Suppression and Cryogenic Liquid Spill Protection, and will be given by Justin Brown, Breakthrough Initiative Leader, and Alec Cusick, Technical Lead, both at Owens Corning. In this webinar, they will discuss considerations and priorities during cryogenic liquid spills at LNG facilities, including thermal shock to concrete and steel, vaporization of liquid hydrocarbons, and radiant heat during potential fires. At the end of the presentation, there will be an opportunity to put your questions to Alec and Justin in a live Q&A session. So I'd like to invite you to submit your questions throughout the course of today's webinar. For those of you that are joining us on a mobile or cell phone, you can access the question box by tapping the Q&A icon at the bottom of your screen. And for those of you using a desktop or laptop, just click on the Q&A icon in the top right of your screen. You can then click Ask a Question, type your question into the box, and click Submit. A quick reminder that everyone who is registered to attend this webinar will be emailed a full recording after today's session. That's all from me for now, so I'll pass you over to our presenters, and I'll see you on the other side for the Q&A session.
Jessica, thank you for the introduction today. Today we will be discussing LNG pool fire suppression and cryogenic liquid spill protection via two of the unique foam glass systems from Owens Corning. I'm very excited about this topic as we will speak through updated large-scale testing that was completed at Texas A&M in Q1 of 2025, in which there are some very interesting results, and we'll share some exclusive videos and outline when the white papers will be presented. Before we dive in, let's quickly level set with an agenda for today's session. First, a brief overview of Owens Corning, priorities during a cryogenic spill, then the two foam glass systems, pool fire suppression and cryospill. After this, we will hand it over to Alec, who will do a deep dive of the testing, which was an update from the 2025 testing that was performed at Texas A&M with their largest LNG basins, and a quick overview of Owens Corning's technical resources, and lastly, we'll close with Q&A. Now, a quick overview of Owens Corning. Owens Corning was formed in 1935 and has been a Fortune 500 company for 71 consecutive years. It is headquartered in the United States. Owens Corning has revenues in excess of $11 billion and over 25,000 employees. We are a global company and operate in over 31 countries. Overall, Owens Corning has the breadth and depth, global reach, talent, and resources to supply all projects, large and small. Lastly, the core of what we do is building a sustainable future through material innovation. This is exactly what we will be discussing today. Next, we shift priorities that occur during a cryogenic spill. There are three key priorities during a spill. First, the reduction of vaporization of any liquid hydrocarbon, such as LNG. Second, the reduction of radiant heat in the event of a pool fire. And third, the reduction of thermal shock to the basin's steel, its rebar, and the concrete. First, we look at the reduction of vaporizations from liquid hydrocarbons. In the event of a spill or release, invisible LNG vapors may drift from the spill location until they contact an ignition source. Recall that liquids must first vaporize in order to burn. The image on the slide illustrates the water vapor of the moving cloud as it contacts the LNG. Prior to ignition, heat can be transferred from the fuel to the walls of the impoundment basin, as well as the environment. Think about the wind and the sun. Therefore, to reduce the chance of a pool fire, an effective mitigation system must limit that pool vaporization. Less vapor, the lower the chance of ignition and a subsequent pool fire. A key point to understand is that the ignition range for LNG is typically in the 5 to 15%. This range might not occur right near the basin and might be carried downwind before finding an ignition source, which is problematic. The fire hazard now widens from the nearby basins all the way to a downwind ignition source that can actually blow off the site. Next, we look at the reduction of radiant heat and the potential for the radiant heat to cause cascading events. The image on the right is from testing done in Spain in 2014, which we just updated with our trials at Texas A&M in Q1 of 2025. If ignited, an LNG fire can cascade into a self-propagating reaction, leading to extreme radiant heat to the nearby environment. After ignition, the radiation feedback from the flame to the pool surface drives additional vaporization rates, and this actually drives the flame to become higher and higher. Lastly, we will discuss thermal shock protection to both the concrete and steel in the basins. Sudden exposure to cryogenic temperatures can negatively impact the load-bearing capacity of the basin, which is, again, the concrete and the rebar or steel. If you recall, LNG is cooled to approximately negative 200 degrees Fahrenheit or negative 160 degrees Celsius. So we can see structural changes that result in reduction of load-bearing capacity when suddenly exposed to these cold cryogenic temperatures. When rapidly exposed to sub-freezing temperatures, concrete can go through multiple processes that cause microfractures, contraction of the solid network of the concrete itself, an expansion of the water as it freezes within the concrete structure, as water phase changes and volumetrically expands from a liquid to a solid. Carbon rebar can be used but becomes brittle at temperatures around negative 29 degrees Celsius, negative 20 degrees Fahrenheit. And certain low grades of stainless steel can tolerate cooler temperatures, such as negative 48 Celsius to negative 54 Fahrenheit, but are uncommon due to pricing with stainless steel versus typical carbon steel in rebars. Next, let's discuss the two foam glass systems from Owens Corning, PFS and cryospill. The base building block of both PFS and cryospill is foam glass. A brief overview for those who are not familiar with this material. Foam glass insulation is a lightweight, rigid material composed of millions of completely sealed off glass cells. Foam glass's properties make it an attractive insulation around cryogenic liquids. For example, low temperature range for the cryogenic hydrocarbons, such as LNG, its high temperature range in the vent of a pool fire, buoyancy on both water and LNG allows the system to float with regards to the PFS system, insulatory properties to prevent thermal shock to the walls and hence the concrete and the rebar, as well as insulating to reduce the vaporization from the walls and the top from the PFS. Foam glass is non-combustible, so in the event of a pool fire, the material itself does not burn, as well as compressive strength so you can walk on the systems without damaging, which is not always possible with many insulation types. Additionally, there are several other properties that are beneficial, such as non-absorbency, it's impermeable to hydrocarbon and water. So with that level set, let's jump into the systems. The first system is the PFS system Generation 2. This again leverages the foam glass insulation as the core material. You can see it in the black. The modules of foam glass are cladded in stainless steel, and this is a patented system. It is a passive system, not an active system that needs to be triggered or reacted. It reacts inherently due to the material properties of the buoyancy on water and LNG. It complements safety programs such as cryospill that we'll speak through as well. So the key of this system is it reduces vaporization, which reduces the chance of a pool fire, and it reduces thermal flux, which is the rate of combustion and the flame height. Next, this chart illustrates the various options to EPCs, owners, and operators. The key is to provide protection against cascading events. For example, the pool fire ignites a nearby LNG tank or process piping. Passive fire mitigation is installed prior to operation and is deemed always available. And as such, it does not require activation. Passive fire mitigation is properly maintained and would be considered to have zero probability of failure to go on demand, which means that regulators view the system in a positive manner, being the passive systems. Active fire mitigation, there's always a chance that it may fail due to a lack of detection or a system malfunction. So there is a probability of failure on demand. The first choice is simply to move the impoundment basin away from any of the process piping. Next, you look to reduce the thermal radiation from the basins, and this can be done in two methods. You reduce the opening of the basin by increasing the depth. EX, storing a fixed volume means you have a depth and you have the flexibility option, which is normally limited by constructability. So you really have a fixed depth depending upon where you are. So the next option is you reduce the radiant heat emitted from the basin, and this can be done with the PFS system, which is a passive system, again, due to the inherent buoyancy of the foam glass material. You can also use the next passive system. You can fireproof any critical equipment with passive insulation coatings. Next, we shift to active systems. You can use fire water, or you also could use high expansion foam systems. So let's jump to the next slide. So this is how PFS works. Again, it is a passive system that is contained in the trenches or the basin. And as LNG enters the basin, it is buoyant. So the modules rise immediately to the surface of the LNG, and it essentially provides an insulating cap on top of the basin or pool to reduce the vaporization. In the event of a pool fire, it does reduce the radiant heat and the flame height. The next system we will talk about is the cryospill system. Again, this leverages the properties of foam glass insulation. You can see here that the black on the basin are the foam blocks, which are adhered to the walls of the basin, and they will be adhered to the floor as well. It is a passive system and provides thermal protection for that thermal shock, and also reduces the vaporization of liquid hydrocarbons because of its insulatory properties. You can see the vapor cloud coming off LNG in a basin without cryospill on NPFS, which is quite large. And if we jump to the next slide, this adds the PFS system, which caps the system as it floats on top. And then as we move to the third slide, you can see that this has cryospill insulation on the walls and PFS. This further reduces the vaporization from the pool. Now let's take a look at an animated video, as I'm a visual learner. Let's see the animation now. This would be an example of an LNG facility. You can see the tanks and the basin. In the basin is where the system is put. First, the cryospill system, which, as we talked about, reduces vaporization and thermal shock. This is added to the walls and floor of the basin. A protective coating is put over top. You can see the cryospill system installed onto the floor, completing all sides and walls. Next, the PFS system is installed on top of a grading system to put the system above the floor of the pool. The PFS system, the pool fire suppression system, again, works to decrease vaporization and, in the event of a pool fire, decrease the radiant heat. You will see LNG enter the basin. The PFS system, being naturally buoyant, begins to rise up and covers the LNG under that insulatory blanket, reducing the vapors on the pool fire, the pool. Also reducing the chance of a pool fire. The last slide before I hand it over to Alec, this is an example of a large export facility in the Gulf of Mexico and shows you have the large tank in the back, but this is a system that utilizes both cryospill and PFS. And you can see that system, this has been, water has been inputted into the basin post a weather system. And you can see that the whole PFS system rises in unison and helps demonstrate that the system works on both water as well as LNG. Now, let me get ready to hand it over to Alec, who will do a deep dive on the 2025 LNG fire testing that was done at TEEX. Alec, over to you.
Thank you very much, Justin. Well done. And thank you, everyone, for joining us today. Excited to jump right into our topic, which is the recent testing we had done around the PFS system that Justin just went over earlier this year at Texas A&M's TEEX facility. So starting off, the setup that was put in place for this testing was that we utilized the largest concrete basin at Texas A&M's Engineering Extension Service facility. This concrete basin measures 22 feet by 33 feet by 4 feet deep. Within this basin, we conducted 2 live LNG burns, 1 control burn with no PFS system, and then a test burn with the PFS system installed. For each burn, we started off by utilizing 12 inches of LNG, pouring it into the basin and then igniting it. And I do want to note that the facility's trained LNG professionals handled all LNG delivery, ignition, and extinguishing of fires. And our primary objectives throughout this test were to measure the LNG burn rate reduction, as well as measure the flame length reduction after installing the PFS system. Here you can see some photos of the testing setup. On the left, you can see the process of the PFS system being installed. It is a pretty easy process to go through. You start at one corner and you space the modules accordingly, and you eventually end up with a nice continuous surface of stainless steel that you see the tops of those PFS modules. On the right, I'd like to call attention to a specially designed thermocouple tree that we made just for this test. This is a apparatus made of 316 stainless steel that sat in the corner, and on the back side of it, thermocouples were attached at every half-inch increment. The function of this thermocouple tree was to measure the rate at which the LNG dropped during each burn. So as the LNG falls, as the vaporization takes place and it's burned off, we can see the temperature profile drop down as thermocouples get exposed from being in cryogenic temperatures to suddenly being exposed to the fire. And that allowed us to capture the data we were looking for. Here you can see live video footage showing the comparison of both burns from the test. On the left, you see the unmitigated burn with no system in place, and the right is with the PFS system installed. Here you can visually see a significant reduction that takes place for flame height between the two tests. And this is a significant consideration for specifiers who are designing safety plans for their LNG facilities. So as part of the data analysis that took place after we finished conducting these tests, we utilized cameras set up around the perimeter of the basin and used software to analyze the flame length and flame tilt across over 10,000 video frames from the video footage that we captured. We then used that analysis to determine the average flame length between both tests. We then also determined the average burn rate of LNG using the thermocouple tree data that we discussed a few slides ago. We then concluded the reduction of each, both with and without the PFS system. And as you can see here on the bottom, after the PFS system was installed, we saw a reduction in flame length of about 87% and a reduction in LNG burn rate of about 85%. So very significant numbers. One next step that we are pursuing now using this data, CFD or computational fluid dynamic softwares are commonly used in the industry to model flame heights and radiant heat profiles of potential fires that could occur within these types of impoundment basins. This modeling helps facilities determine the potential consequences of an unintended LNG fire. We've utilized Fire Dynamics Simulator, or FDS, which is a type of CFD software, to model the unmitigated LNG burn from this test. And what we saw was a strong correlation between the observed flame and modeled flame in FDS. And that gives us confidence that we observed and received good data from the LNG burn that we did. Moving forward, we are working with outside CFD users and supplying them with the data from our test in order to enable them to more accurately model potential LNG fires that have been installed with our PFS system in place. What I'd like to show now is one more video showcasing a unique learning points from this test, which is how unwieldy an unmitigated LNG fire can be. The video you're seeing now shows the third attempt from the facility's trained professionals at extinguishing the unmitigated LNG fire. We frequently speak with facility owners and specifiers as a part of designing this PFS system. And we found that some specifiers are under the impression that a quick enough firefighting response time can mitigate the risk of cascading events or of things going wrong should a fire break out. Another way to put it, if we put out the fire quickly enough, nothing bad will happen. Well, after 6 minutes of the unmitigated burn, the decision was made to extinguish the fire and conclude the test. Here you can see over 2,000 pounds of dry chem material was used to extinguish this fire. But what we saw was that the concrete and steel surfaces remain hot enough to continuously reignite the escaping gas vapors. It got to the point where eventually the decision was made to let the fire continue until the LNG fully consumed itself. And this is in stark contrast to the PFS test, which was easily extinguished using dry chem when the decision was made. So a learning point from this whole ordeal is that extinguishing an unmitigated LNG fire should not be considered a foolproof solution for a facility safety plan. So next steps for us, we have multiple white papers that we're excited to be presenting this fall that will cover a lot of these topics in even greater detail. We will be presenting them at the 2025 Mary Kay O'Connor Safety and Risk Conference. That will be taking place October 21st through 23rd in Houston, Texas. And there are 3 white papers that will be presented as a part of a total session on LNG fire safety. First, there's the PFS testing results, which will go into greater detail about the results, which we previewed here. That will be a white paper titled Experimentation on the Effectiveness of Pool Fire Suppressant for LNG Pool Fires. Also, we will be diving into the future of FDS modeling, covering how our data can be incorporated into future CFD softwares. That'll be titled FDS Validation for LNG Pool Fire with Pool Fire Suppressant. And then finally, there will be a third white paper presented by the LNG experts at TEEX's facility, and they'll actually be covering some of the lessons learned from them when trying to extinguish the unmitigated fire we just saw. And that will be titled Fighting LNG Pool Fires, a First-Hand Report. Finally, I'd like to point out that the PFS system, both between our Gen 2 system that we've covered today and our previously and now discontinued Gen 1 system, this system's been utilized in multiple regions around the globe over the past multiple decades. While LNG regulations may differ depending on country or region, the need for passive and reliable safety measures at these types of facilities does not. So wherever your facility may be, PFS system may be the right solution for you. And now I'd like to wrap things up really quick just by covering some additional technical resources that Owens Corning has available both for these systems as well as for other insulation. Starting off, we maintain over 125 different commercial and industrial insulation system guide specifications, including for both PFS and cryospill that we've talked about here today. These documents are used as a guide for engineers, specifiers, contractors, and facility owners to aid in the design, installation, and maintenance activities of these systems. They include products, detailed drawings, and installation guidelines for each system. And we're also happy to review client specifications and provide advice to how they can improve their specifications when necessary. I'd also like to point out that Owens Corning is a global leader in terms of customer training programs that we offer. We have multiple training centers available to the public as well, including our brand new Pasadena, Texas training center, which you can see in pictures on the right. We also have locations in Yantai, China, and Tessenderlo, Belgium. These provide purpose-built, distraction-free learning environments where we can offer a wide range of train simulations to enable contractors to have confidence when installing our systems. Furthermore, we're also happy to travel out to the field and provide customized training at a specific client's location or a project facility. This could enable training to take place with more staff in less time and avoid a lot of inconvenience and travel costs associated with it. And this is a global offering, and we'd be happy to have a conversation wherever your project may be as to how we can offer training. Finally, I'd like to point out that we at Owens Corning maintain and utilize a full suite of proprietary thermal calculation software to help aid in the design for those who specify our insulation systems. If you have questions around interface temperatures of your concrete basins during a spill, potential reduction in LNG vaporization, or general questions around insulation system thicknesses, we'd be happy to assist with a thermal calculation report tailored to your specific application. With that, I'd like to thank everyone for joining us here today on behalf of both Justin and myself, as well as thank you to Jessica and LNG Industry for the opportunity to present these topics today. For additional questions you may have, feel free to reach out to our technical services and training team at the phone number or email you see listed on screen.